Hello everyone, so welcome to another LeetCode question. Today we'll be solving search insert position. It's a problem of searching. So let's read the question very carefully. So we have been given a sorted array of distinct integers. So array sorted and we have distinct integers and we have a target value, and what we have to return is the index if the target is found in the array. If not, we have to return the index where it would be if it were inserted in order. Okay, and we have to write an algorithm with big of log n complexity. So no linear complexity, we have to write a log n time complexity. Let's go through a few examples to enforce our understanding of what the question is asking. So we have been given a nums array of 1, 3, 5 and 6 and the target is 5. So where would we insert this 5? So we can insert it here at position 2, right? This has been given the question that return the index if the target is found. If not, if we look at here, the target is 2 and the nums is 1, 3, 5 and 6. So 2 can actually be inserted here just after 2, just after this 1. Okay, so the position will be 1. So in this case, we'll return 1. And the target is 7. So in this case, where will be insert 7? After 1, 3, 5 and 6. After 6, we will insert 7 in the correct order, and the position of 7 would be somewhere here, and which is 4. Okay, so this is what the question is. So discussing about the intuition for here, there are 3 things that is given to us. One is obvious that we have to find a position, search position. We are given a sorted array of distinct integers and the time complexity should be log n. So these 3 things are actually the ideal candidate for a binary search. Let's discuss what does a binary search look like. So let's think here, like we have an array nums 1, 3, 4, 8, 20 and 50, and the target that we are looking for is 20. So what we do in binary search, we have a left marker, we have a right marker pointing at the end index of the array, left is pointing at the first index of the array, and we calculate a mid. The mid will be 2, right? So we see that our target is 20, and is it equal to the number at mid? Target is equal to number at mid? No, it's not. Target is actually greater than the number at mid. So where we look for now, we look in the right portion of the array, which is at 8, 20 and 50. Okay, so now my left will become 3, and my right will become 5, right? And my mid will become 4. And now if you look at it, this is actually equal to the target. So we can return this position, which is 4. Now let's take a look at another example to enforce our understanding of the binary search. In this case, let's think like we are looking for the target 1. Okay, so the target is 1. The left marker is pointing at 0. The right marker is pointing at index 5. Okay, so the mid will be this. Is the number at mid equal to target? No, it's not. So where we are going to look for, and the target is actually less than the number at mid, right? Target is 1 and the number at mid is 4. So since it is sorted, since the array is sorted, we can look for the left portion of the array. So we have 1 and 3 and the indexes will be 0 and 1. Left will point to index 0 and right will point to index 1. So we are taking this portion of the array. Okay, now what my mid will be? My mid will also be 0, and the number at mid, is it equal to target? Yes, it is. So we can return mid, right? So this is how binary search works. But if the number is not found, what will happen? The left will become greater than right, and in that case we return -1, indicating that we have exhausted the search in the array and we didn't find the exact position of the target in the array, so we can return -1. So this is how binary search works. Now let's think about a solution for this problem. Since it may happen that the element let's say 21 does not exist in the array, but its search position in the array would be 6, right? But if we only employ binary search, in this case it will return -1. So how can we modify our existing binary search solution to take this condition as well? Okay, the first case would be when element in an array exists which is equal to the target value. So in this case, our conventional binary search algorithm should work as it is. Now we know at the end of the binary search, what happens is the left will just cross the right. Okay, the left will just cross the right, and left will be pointing at this number if we are looking for target 21 in this array. So if you look at here carefully, left is what we should return if we have the number but the number is not present in the array, right? Let's try this one. Let's try the walkthrough for this example. We have 1, 3, 6, 8, 9, 20 and 100. Okay, the indexes are 0, 1, 2, 3, 4, 5 and 6, and the target that we are looking for is 21, right? So what my left will be, left initially would be 0, my right will be 6 and my mid will be 3. Okay, how we are calculating mid? Mid is nothing but left plus right by 2. We'll see an example or later on in the code walkthrough that this is not how we should calculate mid, otherwise it will lead to integer overflow. But for the sake of this example, let's consider this thing itself, that left plus right by 2 is actually the mid. So left is 0, right is 6, left plus right by 2 is mid, right? So our target was 21, right? Our target was 21. In this case, my mid is 8. Target is actually greater than this mid. So what we'll do, we will take this portion of the array and search in here whether our 21 target is there or not. So in this case, my left will become 4, right is still 6, right? So let's mark our positions. Left is 4, right is 6, and then my mid will become 5. Now my target was 21, right? So at mid, if we look at carefully, the target is greater than mid. Okay, so we have to look in this portion of the array. So what we'll have, 100, and this index is 6, left is pointing here, right is also pointing at the same index, and mid will also point at this index, right? Now mid is actually 21, mid number at mid is 100 and the target is 21, so 21 is actually less than it. So right has to go 1, we have to look on the left portion of the array. So in this case, what will happen, right will be 5, left will be 6. Okay, so at this point we will terminate our search, it will complete our search, and finally we'll have left as the 6th position, right? And this is what we told, that after the end what we'll have, left will be pointing at the position where the target is to be inserted. So in this case, in the second case, when the number is not present in the array, we can return left. Okay, and we have seen an example why we do so. We can return left. And let's go to the time complexity and space complexity for this. As we know that the time complexity for the binary search in a sorted array is log n, right? So it's log n. And the space complexity, since we haven't used any auxiliary space in our algorithm, only the constant space is used, so big of 1 is our space complexity and time complexity is big of log n. Let's go to the code walkthrough. The code walkthrough is very simple. What we do, we have an array nums and a target, and we have to return the search position. So left is 0, initial index of the array, right is pointing at the last index of the array, and like we do, while left is less than equal to right, while we can still search, we calculate the mid is actually left plus right minus left by 2. Let's take an example here why we do so. So for example, so let's say left is equal to somewhere like max by 2, okay, and right is 3 max by 4. And now if we add both of this max is actually integer max, right? If we do left plus right by 2, so what will this become? M by 2 plus 3m by 4. So if we have 4, 2m plus 3m, this will become 5m by 4, right? So if we had only left plus right by 2, then in this case this will become integer overflow, right? That's why we do right minus left. So if we do right minus left, what we'll have, 3m by 4 minus m by 2, this will become m by 4 by 2. So this will never lead us to integer overflow, right, for this case. So that's why we do left plus right minus left by 2. And like we said, we check if it is equal to the target, the number at mid, we return the mid. If the target is greater than nums at mid, left is mid plus 1. This is the conventional binary search algorithm. Otherwise, we look for in the left portion of the array. If the target is greater than nums at mid, we look at the right portion of the array. Okay, and then what we said is, instead of returning -1 in the conventional binary search algorithm, we will return here left. And the end of the algorithm, what we'll have, we said is left will become greater than right, and our target will become less than num set left, and this will be greater than num set right. So this is what we'll have if the number is not present in the array. So this concludes our algorithm for search position in an array. Thank you.